In this video, we're going to be taking a look at something called one-sided limits and then the idea of continuity. So in order for a limit to exist, right, so the existence of a limit, the left-hand limit and the right-hand limit must be the same. So if we look at this, what it says is let f be a function and let c and L be real numbers. So the limit of f of x as x approaches c is L if and only if, and the way that we read this, it says the limit as x approaches c, and then this little superscript negative means from the left. So the limit as x approaches c from the left is of f of x is L, and the limit as x approaches c, this is going to be from the right, of f of x is L. So if you recall, in order for a limit to exist, both the left and right side have to be approaching the same number. And so this left-hand limit and the right-hand limit have to be equal. So you can see that we note that notation here. The left-hand limit, denoted by this, is the limit as of f of x as x approaches the value of c from the left side, or from values less than c. And the right-hand limit, denoted by this, is the limit of f of x as x approaches c from the right, or values greater than c. And so in order for a limit to exist, the left-hand limit has to equal the right-hand limit. Okay, so let's go ahead and take a look at evaluating some left and right-hand limits and talking about whether limits exist in this example. So we're asked to find the left-hand limit, the right-hand limit, the actual limit, if it exists, and the value of our function at c. So that's what this means. For every value of c using this graph here. All right, so when c is 0, what is the left-hand limit? Well, we don't have a graph to the left of 0, so we can say that that does not exist. We'll use D and E for does not exist. What is the limit as it approaches from the right? So as we're approaching 0 from the right, my graph is going up to 1. What is my limit at 0? Well, because there's no left-hand limit, this does not exist. And then what is the value of my function at 0? So when I go to 0, what is the value of my function? It's a closed point at 1, so its value is 1. What about when c is 1? So the limit as x approaches 1 from the left. Now remember, when we're talking about limits, the limit can exist even if the function isn't defined at that value. So as I'm approaching 1 from the left side, my function is getting closer and closer to 0. At 1, it's not equal to 0, but that's what it's approaching from the left side. So that would be my left-hand limit. It would be 0. From the right side, when I'm approaching 1 from the right side, my graph is up here. And it's staying constant, and it's getting closer and closer and closer to 1. Now, do these two match? Is the left hand and the right hand equal? If not, then the limit does not exist. What is the value of my function at 1? So f of 1, it's closed up here at 1. What is the left-hand limit at 2? So if I go to 2 here, as I approach from the left, 2 from the left, my graph is getting closer and closer to 1, right? Closer and closer to 1. Now at 2, it's not equal to 1, but we'd ignore this for right now when we're talking about the limit. So what is it getting close to as I'm approaching 2? So it's getting close to 1. What about from the right side? So it's coming from above, and it's getting closer and closer and closer to 1 as I approach 2 from the right. So these two match, so that means the limit does exist, and the limit is 1. But the value of my function at 2 is not 1, it's 2. So the limit exists at 2, but the value of the function is not equal to the limit. You can see that here. What about at 3? So at 3, from the left, right, as I approach 3 from the left, my graph is going up to 2, so it has a left-hand limit of 2. As I approach 3 from the right, my graph is going up also again to 2. Since these two match, that's the limit, the value of my function at 3 is also 2. So all of those are the same. All of those are the same. What about at 4? So as I approach 4 from the left, my graph is getting closer and closer to 1. Since I don't see my graph to the right, we assume it does not exist there. So the limit as I approach from the right doesn't exist because the graph doesn't exist there. Since these two are not the same, that means our limit does not exist. And that means, does not exist. And the value of my function at 4 is 1. So we have a closed point there at 1. Okay, so what's the point in doing all of this? Well, the idea that the left hand and the right hand limit are the same means that the limit exists. And if we throw in the added bonus of the value of our function equaling that value, equaling the value of the limit, then that gives us the idea of continuity. So continuity, informally, we can say that a function is continuous, and I'm sure you've heard this or used this idea before. If you can draw the function without lifting up your pencil from the paper around that point. But the formal definition of continuity is a little bit more nuanced, and these three pieces have to all be met in order for us to be able to say officially that something is continuous. So in order for a function to be continuous, right, continuous at some point, the following three conditions must be met. So first, the function has to be defined. If there's a hole, if it's not defined at a value, it's not continuous. The limit must exist, which means the left and right hand limit, right? The left and right hand limit have to be the same. And not only that, in order for it to be continuous, the limit of our function at c has to be the value of our function at c. So these three things must be true and must always be shown to be true before we can say something is continuous. So furthermore, we say that a function is continuous on some open interval if it's continuous at every point on that interval. And if a function is continuous on the interval from negative infinity to infinity, we say that it's continuous everywhere. Some functions that fall into this category of being continuous everywhere would actually be every polynomial function. Every polynomial function is continuous everywhere. The sine and cosine functions are continuous everywhere as long as their arguments are defined. So those are a couple examples of functions that are continuous everywhere. Now, if something is not continuous, we can say it's discontinuous or not continuous. Either of those is an okay term to say. But discontinuities fall into three categories. So there are removable discontinuities, jump discontinuities, and infinite discontinuities. Removable, jump, and infinite. So what is a removable discontinuity? A removable discontinuity just means we can actually make this a continuous function by getting rid of or redefining our function at that one spot, right? So we can see that this graph is continuous everywhere except for this one spot, right? So the limit as x is approaching 2 looks like it's up here at around 3 or something, but the value of our function at 2 is 1. So because this is not, the limit does not equal the value of the function, it's not continuous. But if I were to say, okay, instead of the value of our function at 2 being 1, if I redefined it to be 3, then my function would be continuous. So I can remove the discontinuity. That's why it's removable. A jump discontinuity basically means that as you approach from the right and the left, you approach two different numbers, and it's like your graph is jumping. There's a gap and it jumps. An infinite discontinuity is when your graph on either side is approaching infinity. So that would be an infinite discontinuity. Now, one thing to note is we can call the jump discontinuity and infinite discontinuity non-removable. These are non-removable because we cannot just simply redefine our function at the point where it's not defined to fix the discontinuity. So these are non-removable discontinuities. Okay, so let's take a look at this example and describe the type of discontinuity that is shown, and then explain which condition of the definition of continuity is not being satisfied. Okay, so we want to find what kind of discontinuity happens at -3. So -3 here. We have a vertical asymptote, and you can see from the left, my graph is approaching positive infinity, and then from the right, my graph is approaching negative infinity. So this has a infinite discontinuity. And there's a couple, it actually doesn't satisfy a lot of, actually it doesn't satisfy any of the continuity conditions, because the function's not defined at -3. The function is approaching different values, so the limit does not exist at -3. So all no conditions are satisfied. None of the conditions of continuity are satisfied. Okay. What about at x equals 1? So here at 1. As I approach from the left, I see that my graph is approaching a y value of 1. And as I approach 1 from the right, I can see my curve is up here approaching somewhere at about 2.5. So they're approaching two different values. You can see there's a gap in our graph, so this is going to be a jump discontinuity. Our function is defined, but the limit does not exist. So the limit does not exist, so that means the second condition does not hold. So the limit does not exist at x equals 1. What about at x equals 4? So as I approach 4 from the left, my curve is up here at about 3.5. And as I approach 4 from the right, my curve is up here again at about 3.5. They're approaching the same value. But the value of my function at 4 is 2. So in this situation, the limit does not equal the value of my function. So this would be a removable discontinuity, because if I redefined f of 4 to be whatever, what is this, like 3.5, then that would be that would make it continuous. So we can say that the limit as x approaches 4 of f of x is not equal to f of 4. So that's the condition that is not met for the continuity here. And then at 6, again, it's going to be removable. There's not even a value that it's defined to be, but it still is removable, because we could just define the value at 6 to be whatever it is, to 1.5. But we can say it's a removable discontinuity, and it's not continuous because f of c does not exist. So because it's not defined there, it can't be continuous. All right. So in example 3, part A, we need to figure out, are these functions continuous at each given value, and then explain our reasoning. So we're trying to find the continuity at, determine if it's continuous at x equals 2. So that means as I approach from the right and the left, the limits have to be equal to 2. The limits have to be equal at x equals 2, and then the value of my function at 2 has to equal my limit. So let's look at the left and right hand limits. So what is the limit as x approaches 2 from the left of f of x? So if I'm looking at numbers that are less than 2, which piece of this piecewise function am I using? Well, I would be using this part of the definition here, because values of x less than 2, that's what this means here. And this chunk is a line, so it's it can be evaluated using direct substitution. So if I plug in 2, and I'm approaching 2, right? So I'm going to plug in 2 as my value in for x. So if I plug in 2, 2 minus 2 is 0. So the limit from the left is 0. What is the limit from the right? The limit as x approaches 2 from the right of f of x. So that means I'm looking at values of f that are greater than 2. So for that, I'm using this part of my definition. So it's going to be 2 minus x. Okay, so again, if I'm approaching 2 from the right, I'm using this part. So let's plug in 2 for x. 2 minus 2. That again is 0. So those are the same. So that's good. That means that the limit, so this tells me the limit as x approaches 2 of f of x is 0. So we know the limit exists. But what is f of 0? What is, sorry, not f of 0, f of 2. F of 2 is, well, when x is equal to 2, the y value is 1. Since these two are not equal, this is not continuous. Now, what kind of discontinuity would this be? This would be a removable discontinuity because the limits approach the same value, but the value of the function is not the same as the limit. Okay. Let's look at part B. Determine if this function is continuous, and then again explain your reasoning. So we're looking at x equals 3. So first we want to find the limit as x approaches 3 from the left of g of x. So plugging in 3, 1/3 times 3 is, we're looking at limits, values from the left, so that means we're looking at values less than 3, so we're going to use this part. So plug 3 into this. So 1/3 of 3 is 1. 1 plus 4 is 5. And then look at the limit from the right. The limit as x approaches 3 from the right of g of x. So 3 from the right, values greater than 3, we're using this part. So 2 times 3 minus 5. 6 minus 5 is 1. So these two pieces are not equal, right? This is not equal to this. Because these are not equal, this tells me that the limit as x approaches 3 of g of x does not exist. Therefore, g of x is not continuous. All right. And then in part C, we're asked to find the limit at x equals 4 for h. We're asked to determine if it's continuous at x equals 4 for h. Now, something that's kind of interesting and a quick little hack here, if we look at the conditions of this piecewise function, we notice that this is saying this is true for values of x less than 4, and this is true for values of x greater than 4. This function is not defined at 4, right? So h of 4 does not exist. And so because of this, right, h of x is not continuous. I actually don't even have to look at the limits. I don't even have to look at the limits because the function doesn't exist at 4, so it can't be continuous at 4. Now, if we did look at the limits, if I plug 4 in here, half of 4 is 2, 2 plus 1 is 3. If I plug 4 in here, negative 4 plus 7 is 3. So the limit of h of x as x approaches 4 from the left was 3. And that is also the limit as x approaches 4 from the right. So they do have the same limit from the left and right, which means the limit does exist at 4. But because it's not, because h is not defined at 4, we know that it's not continuous. So we actually didn't even have to evaluate the limits here to talk about the continuity. Okay, so this last one what is happening here? So the limit, so first of all, what is f of 2? F of 2 is 1 over 2 squared is 4. 6 times 2 is 12, so minus 12 plus 8. This is going to be 1 over 0. 1 over 0. 1 over 0, that's not defined. So that means that f of 2 is not defined. And therefore, f of x is not continuous. Now, if you wanted to find the limit, this is actually going to be an infinite discontinuity because what we actually get here is a vertical asymptote. So if you wanted to evaluate the limit, we could factor f of x to be 1 over x minus 2 times x minus 4. So if I wanted to evaluate the limit around 2, I would actually have to use like a table of values and pick numbers like 2.1, 2.01, 2.001, 1.9, 1.99, 1.999, and see what's happening at either side of that and see what those are approaching to actually look at those limits. And they're going to be going off to like positive or negative infinity when you do that. So the limits technically wouldn't exist there either. But if you wanted to see how it was unbounded, you would have to use like a table of values to evaluate that limit.